Exercise 1.1, question 1. Use the Euclid's division algorithm to find the HCF of, and then you have three parts. Each part has two numbers. You want to find the highest common factor that these numbers have. Now, what you have to do here is not just any method to find the HCF, you have to use a specific method. It's the Euclid's division algorithm. It's a specific series of steps that you have to follow. Now, before I discuss what this Euclid's division algorithm is all about, I'll talk about what this is based on. So, this is based on the Euclid's division lemma. A lemma is what? It's just a proven statement. It's something that is true. It is a statement that is then used for proving another statement. So, this is what you take as a true statement. Like this is true, and then based on this, what all can you say? So then you move on to your other things. But let's discuss what this lemma is all about. Let's read it together. Given positive integers a and b, so any two integers in the world you're given, a and b, there exist unique integers q and r satisfying a is equal to bq plus r, and then there's one more relationship telling you about the range of r, that r has to be less than b and it has to be greater than or equal to 0. Now, right now, this might be looking very, very complicated because you have four unknowns in this. You don't know A, you don't know B, you don't know Q, you don't know R as well. But this is something you've been doing for years and years now. This is just your long division process. Let me tell you how, by taking four numbers instead of A, B, Q, and R. Consider this simple division with two numbers. Let me just take 15 and 2. So if I have two numbers, I will take the greater number inside as my dividend and I will divide it by 2. Now when you do that division, what do you get? This is 2 sevens are 14, and then when you subtract, you're left with 1. Since 1 is smaller than 2, you cannot divide it any further and you're done. Now you will notice a relationship between these four numbers. Which four numbers? The dividend, the divisor, the quotient, and the remainder. We can express the relationship as an equation. This is the relationship. So 15 is equal to 2 times 7. So you multiply these two, the divisor and the quotient, and then you add the remainder to it. You will get the same result as your dividend. Just verify this. 2 times 7 is 14 and 14 plus 1 is indeed 15. So this is true. So the relationship I've written here, let me just write it in general terms. What we have is this. Dividend, which is what goes inside, is equal to the divisor, which is the number by which you divide, multiplied by the quotient, which is 7 here, and then you add the remainder to it. So this is the core result, the core principle that works for every single division problem. You can pause the video and take any two numbers and divide them and verify this result. It has to happen. Now the result that you see here, it's just that you don't have numbers. But again, think about it. You have two numbers given, A and B. You are dividing one number by the other. So suppose A is the dividend and B is the divisor. Now when you do this division, there has to be some quotient, right? So say that is Q only. Since I don't know the number, I'm just using it as Q. You do your whole division, and ultimately when you subtract at the last stage, you get the remainder, which is something that you cannot further divide. But even now, this result that you saw for the general case still has to work. So for my case, my dividend is A. So this first thing here becomes A is equal to, my divisor here as you see is B. So this place is filled by B, multiplied by the quotient, which is Q for me, plus the remainder, which is R for me. This is exactly the result that you see here. A is equal to BQ plus R. Isn't that super simple? And then this last bit about the range of r is also obvious. You have a remainder. That remainder has to be less than the divisor. Otherwise, why would you stop dividing? You would still go on, right? Here also you see 1 is less than 2. So this happens always. Your remainder is always less than the divisor. It can be 0 if nothing is left, or it will be more than that. So this is how you read this sign. The remainder is greater than or equal to 0. Okay, now finally we're done with the lemma. We ultimately have to come to this algorithm which we need to solve this question. So an algorithm is what? What does this word really mean? It's actually a series of steps. It's well-defined steps. You know what to do after the first step. So it's not as if we're thinking every time we do something. It's well-defined. This algorithm is a technique that you will use to find the HCF, or the highest common factor, of two given integers. Now, how exactly you use this, what exactly are the steps, I'll discuss that through these three parts here. So let's start with part 1. Alright, here is part 1. We need to find the HCF of 135 and 225. Here on the right hand side is a page from the book which gives you the exact steps to follow. So I will read each step and show you its application with this question. So it's very difficult to understand these steps with just these C and D and Q and R and all of these unknowns. But when you see it on numbers, the method will become a part of your thought process. So here we go. We have to find the HCF of two numbers, say C and D, with C greater than D. So you'll always be given two numbers then, whose HCF you have to find. I'll tell you what happens if it's three numbers. Now here it's two numbers. I have two numbers here. So one of them is C, the other one is D. But they're saying C is greater than D. That means you always take the greater number to be C. So in my case, which one is the greater number? It's 225. That means 225 is my C and 135 is D. That does not really matter. It's important only because we're trying to understand the steps in this first part. From the second part onwards, I will not talk about C and D at all. So for me right now, this is C, this is D. Now what happens? Step 1. It says apply Euclid's division lemma. That is why I discussed it in so much detail. Apply the lemma to C and D and you will find quotient and remainder Q and R such that this happens. Now you know how you get the quotient and the remainder, right? You've been dividing things for years. You just divide the bigger number, which is 225, by the smaller number, which is 135. Now when you do this, you will realize 135 times 2 will be 270. So that will be a little too big. So you just multiply it with 1 only. Then you write it here. You subtract, you borrow here. You know this. This is 90. Now since 90 is smaller than 135, I cannot divide any further. So this is step 1. That's it. You have to find the quotient. This here is your Q, and you have to find the remainder. This here is R, such that your remainder is greater than equal to 0 and less than the divisor. Clearly this is happening here, right? 90 is definitely less than 135 and it is greater than or equal to 0. So your condition is met. Now what do I do here? I have to write this relationship using the Euclid's lemma. So I will write it like this. So 225, my dividend, is equal to 135, which is the divisor, times the quotient plus the remainder. You know this. This is exactly what we saw previously. Let's read on. Next it says, step 2. If R is 0 at this stage, if the remainder is 0, then D is the HCF. D means the divisor at this stage itself will become the HCF. But if R is not 0, then we apply the division lemma one more time to D and R. What are D and R for me? D and R are the divisor and the remainder that I have. Now as I see here from step 1, my remainder really is non-zero. So I'm not done yet. It was if it is 0, then D is the HCF. But if not, you apply the lemma one more time to D and R. So I have to apply it one more time to 135 and 90. So let me erase this one first. Alright, now between 135 and 90, which you should be able to see from this equation also, this is what you have, this is the divisor's place, this is the remainder's place. You again divide the bigger number by the smaller. So you will divide 135 by 90. Yet again, this will be one time only, 9 twos are 180, so that will be a little too big. When you subtract, it is 45. And again, you cannot divide any further because 45 is already less than 90. It does meet the condition. It is less than the divisor and greater than equal to 0. Then you see again what happens at step 2. Step 2 was again R0, then D is the HCF, otherwise go on. And how do I know I still have to go on? I see that in step 3. It says continue the process, just keep going and going till your remainder becomes 0. So even now my remainder, which is 45, is not 0. That means I have to go on one more time. And what do I know about that yet again? I have to apply the division lemma again to D and R, to my divisor and the remainder. So one more time, once I do that, I'll do it on 90 and 45. But let's first write this down. So you have 135 is equal to 90 times 1 plus 45. So this way you will be able to see every step in our solution. Now you're picking up this D and this R. So let's do that division here only. You divide the big number by the small number. 45 twos are 90. Perfect division. Remainder is 0. Finally, we got to the stage where we had to go. At step 2, you see, if remainder is 0, then D, which is the divisor at that stage, which is 45 for us here, will be the HCF. So for my case, let me just first write it this way. 45 times 2 plus 0. So the stage where your remainder has become 0, at that stage your divisor is 45. This. So this is the final HCF that you were looking for. So finally the HCF of 135 and 225, you can express it this way, keeping a comma between them. The HCF is 45. And here we are done with part 1. Now this part took a while because we were doing this method for the first time. But watch this again and again to understand this solution in complete detail. So then when we go to parts 2 and 3, it will be much smoother. I'll just keep applying the lemma till I get my remainder equal to 0. Let's go and look at part 2. Okay, here's part 2. The numbers are 196 and 38,220. So I'm going to do the division and then resume the video. Alright, here is the division. So my dividend was 38,220 and my divisor was 196, and the very first time I did the division, my remainder came out 0. So I'm already here at step 2, you see, after using the Euclid's division lemma. Let me just write it using the lemma as well. So you have 38220 is equal to 196 times 195 plus 0. So the stage where you want to have the remainder equal to 0, you do not have to do it 3-4 times to get to that stage. We had it right here in the first division, and we know that when this happens, the divisor at that very stage, so 196 for us, this itself is the HCF. And so this was a quick one. Yes, the division itself takes a little bit of effort, but again, you didn't have to do multiple steps. So part 2 is done. Let's move on to part 3. Here's part 3. The numbers are 867 and 255. You know the drill now. You have to divide the bigger number by the smaller number. Yet again, pause the video, do the division, and then see it again. You'll see my division done by then. Alright, so here is division stage 1. I hope you have the same and didn't make any calculation errors. So you see the remainder at this stage is 102, which is not equal to 0. And that means, that tells me that I have to apply my lemma one more time. So let me just first write down what I have here. 867 is 255 times 3 plus 102. And now you know you have to apply the lemma on which two numbers? On the divisor at this stage and the remainder together. So you will now divide the bigger number, which is 255, by the smaller number, which is 102. Yet again, do it and then start. Alright, so this is what you should get if you divide these numbers. The remainder, as you see here, is 51. So again, it's not 0. That already tells me that I have to do more. I'm not yet done. So let me write this stage down. 255 is equal to 102 times 2, which gave me the 204, and then plus 51. So since it is not 0, I have to apply the lemma one more time on these two. Which two? The divisor at this stage and the remainder at this stage. So one more division now. There you go. This time the remainder is finally equal to 0. So this is the stage where you will get your HCF without doing any further work. So the HCF is the divisor at this stage. So 51 is your answer. Let me still just write it using your proper lemma. So 102 is equal to 51 times 2 plus 0. So this is the stage where your remainder has become 0. And so finally, the divisor at this stage, 51, is the HCF. So this is our final answer.